All right, let's talk about conservation of energy. Now, in order to understand what we're talking about when we're talking about the law of conservation of energy, the first thing we want to talk about is what we call total mechanical energy. So, your total mechanical energy, right, is simply the sum of your kinetic and potential energies, right? So, it's the energy present in a system that is capable of doing work. And so, the law of conservation of energy tells us that your total mechanical energy, meaning the total amount of kinetic and potential energy present beforehand, has to be equal afterhand, right? So, your initial total energy has to equal your final. And again, this is when we're talking about, say, a closed system, right? So, a system that has no outside force doing work on it. So, in the absence of these outside forces doing work on a system, your total energy has to equal, or your total initial energy has to equal your total final energy. Now, that doesn't mean that your individual energies can change, right? Potential can become kinetic, kinetic can become potential, but that total energy needs to remain identical, right? So, if we want to expand on this, our initial kinetic plus our initial potential is equal to our final kinetic plus our final potential. So let's take, for instance, let's say you had yourself a pendulum, and we'll draw three different stages of the pendulum's trip. So the pendulum takes a path like this, right, and it's going to swing back and forth. Well, at either end, right, all of that energy is present as gravitational potential energy, right? It's in an elevated position and it's not moving. Now, down here at the very bottom of its swing, though, right, all of that energy, all of that potential energy up here has been converted to kinetic, right? So as your pendulum swings, it loses potential energy, gains kinetic energy because it's gaining speed. Down here at its lowest height, we could say that it's all kinetic energy. And then as it swings past your equilibrium position, right, that kinetic energy shrinks as it slows down, and as it raises in altitude, it gains potential energy. Now, your overall total energy must remain constant in the absence of an outside force, but those individual energies can change, meaning, again, your potential can become kinetic, kinetic can become potential. But the key here is that that total energy, your total mechanical energy, must remain constant. Now, a lot of people, in our daily lives, let's say again we're talking about this pendulum. If you've got a pendulum running in your house, right, eventually it's going to stop, right? Well, that's because you're not dealing with a isolated system, right? What you're dealing with there is a system that, well, you've got work being done on it. Say whatever your pendulum is hanging from, right? There's some friction there as that pendulum swings back and forth, right? And so any of this energy that we find disappearing is typically being converted into some other form of energy, whether it's sound, um, whether it's light, whether it's thermal energy, right, due to friction being involved. So if you're seeing energy disappearing from a system, that's evidence that your system is not isolated, right, and that you've got some outside forces working there. But again, when we're dealing with problems here, we consider these systems to be isolated. Your total energy must remain constant. So let's take a look at example 1010 in the notes. So at the county fair, Katie tries her hand at the ring the bell attraction. She swings the mallet hard enough to give the ball an upward initial speed of 8 meters per second. We want to know, will the ball ring the bell 3 meters from the bottom? Now, the nice thing with some of these energy conservation questions is there's multiple different ways to prove whether or not something will happen. Right? And it depends on just your perspective. So, good place to start, and you'll notice this in all of the old free response problems, right? They are always going to give you an image, right? So always just start with the basic sketch of what's going on here, right? So we've got that ring the bell attraction, right? Here's Katie with the hammer, and she's going to hit that pressure plate down there, and we want to know if she's able to ring the bell. Well, we know that there's going to be an initial velocity of 8 meters per second. We also know that that bell is at a height of 3 meters. We know it starts at a height of 0, so h naught would be 0. So basically what we're saying here is that here at the bottom you've got pure kinetic, and then we want to know if that's enough kinetic energy generated for that that plug to actually reach up and hit the bell. Now again, there's multiple different ways of looking at this. So we could calculate what the kinetic energy is, or the speed, right, of the object is at height equals 3, or we could find the maximum height to which it would rise. So let's go over both different ways. So one way we could do this using energy conservation is looking at, again, just a basic statement that energy is conserved. There's always a point for explicitly stating that in Fourier response problems. So make sure that you're being explicit about your energy conservation statement. So let's just first see if the ball is moving at height equals 3 meters. So initially, we've got kinetic energy. And we want to see what happens here at the end. So 1/2 mv naught squared is equal to mgh plus 1/2 mv squared. Now if v turns out to be a solvable number, we know that it's still moving at height equals 3 meters, which means that we know that it's going to hit the bell. Now notice the nice thing about energy conservation. If you've got a constant mass, right, you can cancel that out, make your life easier. So 1/2 of 8 meters per second squared is equal to g times 3 meters plus 1/2 unknown speed. So go ahead, plug that in, and see what you come out with. And you should be coming out with the speed of 1.1 meter per second. Oop, sorry, forgot to take the square root at the end. So 1.04 meters per second. And actually ignore that, I mathed very wrong. And you should be getting, let's see, 2.3 meters per second. So let's be careful with the algebra there. Happens to the best of us. So if it's still moving at 2.3 meters per second at a height of 3 meters, we know it's going to ring the bell. Now alternatively, we can look at it a different way. We could also look at it in terms of, again, starting with our basic statement that energy is conserved. We could say that we're going to take that initial kinetic energy and we're going to say that we don't care where the bell is located. Let's just see what the maximum height that ball could reach, right? So if all of that kinetic energy were transferred to potential, how high would the ball possibly go? Right, so again, 1/2 mv naught squared is equal to mgh. Again, your masses cancel. So 1/2 of 8 meters per second squared equals g times the maximum height. So do your math, solve out for height. And you should be getting 3.3 meters. Right, so we know that there's enough kinetic energy present at the bottom of the ring the bell attraction for that ball to rise a maximum height of 3.3 meters. Right, so that would tell us that yes, if the bell is located at 3 meters, the ball definitely hits it. Right, so there's always multiple different ways that you can solve these energy conservation problems, which is nice. Now I'll be uploading a set of, low tier conservation problems, and then we'll start kicking it up a notch or two as the week goes on. This week and next week, we're going to focus entirely on conservation of energy. Um, Now, the next video I'll be putting out is on conservative and non-conservative forces, but that's going to be very short, and it probably won't be out until the end of the week or next week. Because again, we want to focus our energy, focus our minds on conservation of energy. So, hope all is well. I'll see you in the live sessions.